Okay, so this is lecture 1 for 271. Didn't want to do that. On logic. So what we're going to do is we're going to define propositions and do truth tables. So a proposition is something that's definitely true or false. This is not a proposition. It's an opinion. I think it's true, but other people might think otherwise, not a proposition. This definitely is a proposition. It might be true, it might be false. You'd have to go and look it up. But the thing is, you can look it up, and once you look it up, you can tell whether or not Kirby Puckett once hit 23 home runs in a season. This is also a proposition because it's definitely true or false. Look at the wire that you're looking at, get an amp meter, see if there's current. Either there is or there isn't. So it's definitely a proposition. It's either true or false. So propositions are things that are either true or false. And that's the kind of thing that we deal with in logic. Statements that are true or false. We're not so interested in things that are opinions. So propositions are often represented by the letters P, Q, R, S, T. P colon proposition means that P stands for the proposition. So this notation means that whenever I write P, I mean Kirby Puckett once hit 23 home runs in a season. It makes it writing stuff out a lot easier. So propositions, we can create new propositions from old propositions. Negation, not P. Conjunction, which is and. Disjunction, or P or Q. Conditional, P implies Q, that's the arrow, or if P then Q. And biconditional, P if and only if Q, or sometimes we write that with 2 F's. So each proposition is either true or false. When we combine propositions to get a new one, we want to know when is the new proposition that we're looking at true and when is it false. Oops, didn't want to do that. So keep in mind that if we have 2 propositions, P and Q, there's 4 combinations that we can have. We can have both of them true. We can have the first one true, but the second one false. We can have the first one false and the second one true, or we could have both of them false. So if we're defining a new proposition from 2 old propositions, we have to consider 4 cases to figure out the new ones. And we define our new propositions by means of truth tables. So not P, this is negation, or not P. If I start with a true statement and throw the symbol in front of it, that means that's now a false statement. And if this is false, this is true. So negation just switches the true false. And, well, if I have 2 statements that are both true, then the first one and the second one is true. If I have 2 statements, one of which is false, then it's not true that both of them are true, right? So and means that both of these statements are true, and that gives me that those has to be false. Now, or either is true. And means both are true. So or would be, well, both are true. P is true. So that makes the or true. Q is true, that makes that true, but both false means false. This is usually P implies Q, although we have to be a little bit careful. We define this by saying the arrow symbol means this. True implies true. That's good. True implies false is false. And that makes sense too. You don't want true things implying false things. Again, the English word implies really doesn't deal with these 2 cases. But we have to, if we're going to define the symbol as a new proposition involving P and Q, we have to assign some value to these two cases, and we assign true to them. This is if and only if, and what it does is this is true as long as the two statements have the same value, if they're both true or if they're both false. And it's false otherwise. So, like I said, we have English words for some of these things. The definitions of the symbols are the truth tables, and we have words that are useful to remember those. So this symbol means not. Negation of P is a truth value that P does not. P and Q is and. Both P and Q must be true. P or Q, either one or both must be true. P implies Q. P false and Q true is the only case that makes this false. Remember that the truth tables are the definitions. The words are just ways to remember them. And then P, if and only if Q, is also called a parity operator. If two things have the same value, then P, if and only if Q is true. So here are three statements in English. Can we translate them? Not P would be ice fishing does not start today, right? And negation. If this statement is true, that ice fishing starts today, then this statement is not true. If this statement is false, right, if ice fishing doesn't in fact start today, then this statement, ice fishing does not start today, is in fact true. So P and Q is ice fishing starts today, and Jane buys gloves. P implies Q would be written as if ice fishing starts today, then Jane buys gloves. If ice fishing doesn't start today, then it doesn't actually say anything about what Jane does. So here's a statement. If 2 + 2 = 5, then pigs have rings. Is this statement true or false? Well, this is the statement P implies Q, where P is 2 + 2 = 5. Pigs have wings is Q. But P is false and Q is false. That whole statement is true, which is a little weird, but right, you can look it up in the table. If P is false and if Q is false, then the new statement you get, P implies Q, is true. So Johnson-Bauer, which is the book that I'm kind of following, has a precedence for operators, parentheses, not and or, but I generally use lots and lots of parentheses, and parentheses work the same way they do in algebra, which is do everything inside the parentheses first. So here's a statement. What can you say about the truth of this thing? Well, what we can do is P is true, Q is false, R, I'll just put a little question mark because I don't know about R. So if I plug in these values, T and F for Q and R for P and Q, and then a question mark for R, what do I get? I get not T, and we don't know about R, or P or Q, so that's T or false, so I'm replacing the P's and the Q's with P and Q. And that's a question mark, not question mark. All right, so to evaluate whether it's true or false, we can just plug in T for anything that's true and F for anything that's false. Now, not T, the negation of T is false, so this becomes false, and whatever R is, we don't know what that is yet. Or T or F, and or we need just one of the two to be true, So this becomes true and not whatever R is. False and something, it doesn't matter what this is, right? If one part of an and statement is false, then the whole thing is false. And then finally, false or something. Well, this thing here is an or statement where one part is false. So for this to be true, for the truth value of this statement depends only on what this is, right? If this part is true, then this is false or true, so that's true. If this part is false, this is false or false, which is false. So this has the same truth value as T and not R. This is an and statement. And so T and something means if this is true, the whole thing is true. If this is false, then the whole thing is false. So that means it has the same truth value as whatever R has. So this whole thing has the same truth value as not whatever the truth value of R is. Okay, so we can't actually tell if it's true or false because we need to know what R is and we don't have that information. We can build something called a truth table for this. We have 3 variables, P, Q, and R. So when we build a truth table, P, Q, R, those are our 3 variables. What are the possible states that they can be in? Well, R can be true or false. Q can be true or false, but we're going to write it as TTFF. And then P can be true or false, true, 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 false, 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 false. So there's 8 possibilities there. And I write them in the way I did because I want to make sure that I get all 8. All 3 can be true. One of the 3 can be false. That's this, this, and this. 2 of the 3 can be false. That's this, this, or all 3 of them can be false. So the 2 cases we're looking at up above here is P true and Q false. So in example 4, P true and Q false, that's these 2. Right? And then it depends on what R is. So how do I build the truth table? Well, we start with our parentheses. So we'll start with the not P. If we negate that, we get false, 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 true, 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 true. I'm going to draw sort of a border here. To the left of this border are my inputs, my variables. So there's not P. Then we want to do not P and R. Parenthesis goes there. So when is something true? Well, actually, when is something false? So this will be false whenever either one of these 2 is false. So not P is false here, 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 here. So that means this will be false because not P is false. R is false here and here. And so this will be false because R is false. And these 2 places are where it'll be true because not P and R are both true. So that's this part. Now to deal with this part here, we're going to have a not R, which just means flipping all the values on R. So false, true, false, true, false, true, false, true. And then we need P or Q. Now P or Q is true. If either one is true, it's false otherwise. So it's only false when both are false. So that's these two down here. And otherwise it's true. What's wrong with my eye there? And now we want to join these together with an and. P or Q and not R. So an and is true only when both of them are true. So we're looking at these two columns, not R, P, or Q. We want to see where both of them are true. That's here, here, and here. In the other rows, at least one of them is false. So false there, false there, false there, false there, and false there. Finally, we want to put together this column here. We'll call this A, and we'll call this column B. So A and B. So and statements are false if one of the two is false. So false, 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 false. False here and false there. And it's false. Oh, I screwed up somewhere. Not P and R is false here. There's my problem. I'm gonna have to undo a bunch of stuff there because I made a mistake in defining what my thing is. We want A or B, not A and B. So this becomes A or B. This is false only when both of them are false. So false. A or B is true whenever either one of them is true. So B is true here, so we get a true. B is here, true. That's true. B is true there. A is true here, so we get a true there. A is true here, so we get a true there. Both false gives me a false. Both false gives me a false. Both false gives me a false. And I'm going to put a little vertical line there. This is my output. So technically the truth table is just the inputs column and the output columns. This is all helpful calculations. And note that what we got for example 4, in this row where R is true, this ended up being false. In this row where R is false, this ended up being true, which is what we got up there. So that's how you can build a truth table. Building truth tables, as you go through them, it becomes pretty easy. And you'll see how the patterns go for and or and implies. So two propositions are equivalent, means that the same inputs to the truth table yield the same outputs, right? P equivalent to Q is, 3 lines, or sometimes we just do 2 lines. Formally, it should be 3 lines. So De Morgan's laws are these two, that the negation of an or is an and, but you have to negate the two things. The negation of an and is an or, but you have to negate the two propositions. So why are these equivalent? So P or Q for the left-hand side, we do P or Q, which is true, 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 false. The negation of P or Q flips those. False, false, true. False, 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 true. So this is the left-hand side, which abbreviated as LHS. So left-hand side of the quality. To get the right-hand side, we'll need not P and we'll need not Q. So not P is false, false, true, true. Not Q is false, true, false, true. And then we join those with an and. Not P and not Q. So not P and not Q. And is false if either one of them is false. So that's false. not P is false, so that makes that false. Not Q is false, that makes them that false. And so these two are both true, so that gives me a true. So the outputs, right? These are my inputs. These are the outputs for the left-hand side, the outputs for the right-hand side. They're the same list, false, 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 true. So the two expressions are equivalent, right? I can replace one with the other whenever I want to. So that's one of De Morgan's laws. Implications have got P implies Q. There's a converse, which just means switching the Q and the P, and the contrapositive, which means switching the Q and the P and throwing negations on both of them. So the biconditional can be rewritten in terms of the conditional. So P implies Q is true, false, true, true. That's the basic one. Q implies P. What's the outcome for that? Well, if we have true implies true, that's true. False implies false. If the false is the first term, the Q, then you automatically get true. So false implies false is also true. But then if you have T implies F, right? True implies false, that's the only case that it's false. So P implies Q and Q implies P. That's true only when both of them are true. So it's true here, it's true here, but it's false there and there. So the biconditional P if and only if Q with a double-headed arrow was defined to have this truth table, right? So these are equivalent things. P implies Q and Q implies P is the same as that. Not P implies Q is equivalent to this. So what's the negation of P implies Q is what we're working on here. P implies Q, right? The basic truth table is that. Not P implies Q means that we negate that. False, true, false, false. So this is my left-hand side, the output for my left-hand side. The right-hand side will need not Q, false, true, false, true, and then we need P and not Q. So if we take P and not Q and put them together, true and false is false, true and true is true, false and true is false, false and false is false. So this is my right-hand side. They have the same column, so they're equivalent to each other. You can replace one with the other. So what we see here really is that implication, right, which is and, can be written in terms of the and operator and the not operator. So P implies Q is the same thing as not P and not Q. Right? There's a little bit of an algebra of logic going on there. So implication can be written in terms of and. Sorry, implication can be written in terms of and not. De Morgan's laws shows that or can be rewritten in terms of and not. And so everything, in fact, all logical operatives can be written in terms of not and. And that'll be important when we get to circuit design, because when you want to design circuits, true corresponds to current flowing, false corresponds to current not flowing, or true corresponds to 1 and false corresponds to 0. So finally we have, oh, I forgot. Contradictions and tautologies. I should have an extra bar here because P is our only input. P is either true or false. Not P is false or true. So P and not P. Well, that's true only if both of them are true, and that never happens. It's always false. So this was called a contradiction. P or not P. That's true if either one of these two is true. So true, true. So this is going to be true in both cases. It's always true. So that's something called a tautology. And so that's the first lecture.